Hello everyone. This video is based on a discussion of liquids and solids. So before you dive into this video, make sure that you review Lewis structures and polarity, because in order to look at intermolecular forces, which is going to be a major topic for this video series, you're going to need to know how to build those Lewis structures and how to determine whether or not a molecule is polar. So, intermolecular forces are attractions that occur based on opposite charges between two or more molecules or atoms. Okay, so we've seen charges when we look at ions, right? Cations being positive, anions being negative. But we've also seen partial positive and partial negative charges in polar molecules. So for this example, right, chlorine is more electronegative than hydrogen is. And so chlorine is going to have a partial negative charge, and that hydrogen would have a partial positive charge. Okay, so these partial positive and partial negative charges can be attracted to the partial negative charge, right? This partial positive and partial negative charge can be attracted to each other. Now, we can even have attraction between molecules that do not have stable charges, right? They could just have temporary dipole moments, which we'll talk about shortly. So keep in mind that the larger the charge, the stronger your attraction is going to be. So this is based on Coulomb's equation. And also the longer distance that you have, the weaker the attraction. So when we talk about intramolecular forces, those are your covalent or ionic bonds that we talked about in Gen Chem 1. Okay, intermolecular forces are going to be a much longer distance and therefore weaker attraction, right? So the intermolecular forces are going to be relatively small compared to your intramolecular forces that we saw in Gen Chem 1. Okay, so we're going to talk about several different types of intermolecular forces. Ion dipole attractions are the ones that we'll see the least. Those occur between an ion and a polar molecule. Okay, so you do have to typically have two different types of molecules to have this ion dipole attraction. And one of the most common would be dissolved salts in water, right? Where the salt would be your ion, it would ionize in water, and then water would have your dipole attraction. So the ones that we're going to talk about in more depth are your dipole-dipole attractions. Those occur between polar molecules, and then you can have an especially strong dipole-dipole that we call hydrogen bond. And then we have what are called dispersion forces. So dispersion forces occur in all molecules, but nonpolar molecules only have dispersion because they cannot have dipole-dipole or hydrogen bonding. Okay, and dispersion forces, those are going to occur when we have temporary dipole moments. So just keep in mind that the stronger your attractions are, the more energy that it's going to take to break these apart. Okay, so when we boil a liquid, what that's going to do is provide enough energy to break apart the intermolecular forces, but it won't affect the intramolecular forces, right? So boiling liquids does not break covalent bonds, but it does break apart those intermolecular forces. Okay, and based on the strength of those forces will help you determine what phase that a substance is in at room temperature. So the stronger attractive forces, the stronger intermolecular forces that you have, the more likely they are to be a solid or liquid at room temperature. And then your weaker forces, especially those dispersion forces, those are going to tend to be gases at room temperature. So just keep in mind that the stronger your attractive forces, right, the higher that your boiling points, your melting points, freezing points, and even enthalpy of vaporization, all of those are going to be higher with stronger molecular forces. Okay, so the first one we're going to talk about in more depth are the dispersion forces. So remember, these forces are present in all molecules, but nonpolar molecules only have dispersion forces. And these are caused by temporary dipoles. So basically what happens is that electrons are constantly moving around an atom or a molecule. And so in a moment, electrons may be more condensed on one part of the molecule. Okay, and so that's where you're seeing this partial negative charge on this left-hand molecule to the right, right? So electrons are building up on that right-hand side of the molecule, and what that does is it causes the electrons in a molecule near it to migrate away, right? Because opposite charges attract and the same charges, two negatives, would repel. So the negative charge from one molecule will push the electrons of another molecule away and get this temporary dipole moment where you'll have the positive and negative charges attracting one another. Okay, so that's what dispersion forces are. Temporary dipole moments. Now, dispersion forces, the magnitude of your dispersion forces depends on several factors, and the two that we're going to talk about are polarizability and shape. So polarizability is basically talking about the flexibility or the squishiness of your atom or your molecule, right? So the more volume that you have, the more surface area that those electrons have to move around in. And so when you increase the molar mass or the size of your atoms, you're going to increase the polarizability, and that will result in stronger attractions, okay? So again, the more flexible that your atom is, the more likely that electrons can move around and condense into one space, and then that can increase your attractions. Now, the second way that we can change the magnitude of dispersion forces is by the shape of the molecule. Okay, so the more surface-to-surface contact that you can have between two molecules, the larger your induced dipole will be and the stronger your attraction. So let's see that. The first thing that we talked about, remember, was the size. So if we look at our halogens going down the periodic table, right, we're going to increase in molar mass. We're going to increase as we go down in the size of your atoms or the size of your molecules. And so what that will do is increase your melting points, your boiling points, because remember, attractive forces, the stronger that they are, the higher your melting and your boiling points will be. Okay, and then the other thing that can affect, the other factor that can affect your dispersion force is the shape of the molecule. So the more spherical that your molecule becomes, and that typically happens because of branched chains, the less interaction that you are going to have between two molecules, okay, because you don't have as much surface area. But as we straighten those chains out, we tend to increase the amount of surface area and increase the attractions between those molecules. And so those straight chains, right, are going to have the highest boiling points, highest melting points, and the strongest interactions. Okay, now the second type of intermolecular force that we're going to talk about is the dipole-dipole force. So this is going to occur between polar molecules that have a permanent dipole, right? And we saw that with hydrochloric acid or HCl. Right, okay, so this is based on electronegativities between two atoms. If the electronegativities are different enough, which they are between hydrogen and chlorine, then you have what's called a polar molecule. Okay, and the dipole moment or a dipole-dipole force is going to occur between permanent dipoles that exist in polar molecules. Now, the last type of intermolecular force that we're going to focus on is hydrogen bonding, and hydrogen bonding is a special case of dipole-dipole. Okay, so it is a dipole-dipole interaction. It's just the strongest type that you have. And it's going to occur when you have either an oxygen, nitrogen, or fluorine that are directly bonded to a hydrogen, because oxygen, nitrogen, and fluorine are small and they're some of your most electronegative atoms. Okay, so basically what you have is an extreme dipole moment occurring between oxygen and hydrogen, or nitrogen or fluorine and hydrogen. So what happens is that hydrogen has no other electrons, and so when its electron is pulled away, then you're going to expose that positive charge, that proton that's inside the hydrogen, and this exposed proton can act as a very strong positive charge, attracting electron clouds from neighboring molecules. So, while hydrogen bonds are very strong intermolecular forces, just keep in mind that they're still not nearly as strong as an intramolecular force. Remember, those are your covalent bonds. It's only about 2 to 5% of the strength of a covalent bond. But hydrogen substances that have hydrogen bonding will have higher boiling points or melting points than substances that only have dipole-dipole or dispersion forces. So just as a quick example of this, on the left graph, you have what is expected as you go down the periodic table. So what we have is, we'll just look at the blue line here. We've got H2S, H2SE, and H2TE. So if you look, that is right here on your periodic table going down. And so we expect that as we increase in molar mass that we're going to see higher boiling points, right? That's the trend that we've found. But if you notice, oxygen is actually significantly higher in a water molecule. The boiling point for water is significantly higher than everything else in that group. And that is because H2O, water, experiences hydrogen bonding, right? Whereas the rest in that group do not. Okay, so it goes against the trend that we would expect with molar mass because of the hydrogen bond. Now, one thing that is difficult when you're trying to determine if a molecule has hydrogen bonding is to decide whether or not that hydrogen is directly bonded to a nitrogen, oxygen, or fluorine. So here we have two examples. On the left, we have ethanol, right? And then on the right, we have diethyl ether. So ethanol has an OH group, right? It has a hydrogen directly bonded to that oxygen. Okay, so that can experience hydrogen bonding, and so we see that we have a boiling point of 78 degrees Celsius. Now, these both have similar molar masses, right? They have the exact same molar mass, so we would expect, based on the molar mass alone, that they would have very similar boiling points. But you can see that that's not the case. That diethyl ether on the right has a significantly lower boiling point because that none of those hydrogens are directly bonded to that oxygen. Okay, so on the left-hand side, we do have hydrogen bonding, right? But on the right-hand side, we do not have hydrogen bonding. We only have dipole-dipole, and dispersion forces. Okay, where the strongest is your dipole-dipole. And then on the left, we would say that we have hydrogen bonding, which is a version of dipole-dipole, as well as dispersion forces. Okay, so your strongest force here on the left is hydrogen bonding, and so you expect to have a much higher boiling point, which you see. Okay, real quick, when we're talking about these intermolecular forces with solubility, just keep in mind that similar forces attract and dissolve. So we have this phrase like dissolves like, which means that polar molecules or polar solvents will dissolve polar solutes. Okay, so water will dissolve anything that is ionic or polar or even has a dipole-dipole interaction to it. But nonpolar molecules will dissolve nonpolar solutes, right? So if you have your oils, your greases, those things will dissolve in each other. And your hydrophobic groups, those are going to be what we call your hydrocarbons, right? And your hydrocarbons are things that are nothing but hydrogen and carbon. Okay, so just as a quick summary, remember that dispersion forces are the weakest intermolecular force, but they're going to be present in all molecules, okay, including your nonpolar molecules. Now, polar molecules will have your dispersion forces, but they will also have dipole-dipole attractions, which are stronger than dispersion. And then if you have an oxygen, nitrogen, or fluorine that are directly bonded to a hydrogen, then you can also experience hydrogen bonding, which is the strongest of those three intermolecular forces. And then occasionally you'll see an ion dipole attraction, and remember those are when you have two different types of molecules, one that is ionic and one that is polar. So let's take a second to do a practice example. We're going to list all of the attractive forces that are present in each of these examples, and we're going to circle the strongest force. So for most of us, the easiest way to do this is going to be to draw the Lewis structure. So if you go back, you'll remember that Lewis structures for NCl3, nitrogen is going to be our central atom because it's the least electronegative, and it's also the first one listed as long as it's not hydrogen. Okay, so we know that nitrogen is going to go in the center. It's going to be bonded to those three chlorines. Okay, and if you go back to those general trends that we learned in the last video series, you'll see that halogens, they tend to like to have one bond and three lone pairs. And chlorine is a halogen, okay, so it's going to have one bond and three lone pairs to give it an octet. And then nitrogen likes to have three bonds and one lone pair. Okay, so it's already got the three bonds to the three chlorines, and we add one lone pair. And if you were to count up all of the total valence electrons and double check, you would find that you've used exactly all of your valence electrons and that everything does have an octet, and the formal charge would be 0 for all of the atoms listed. But you can go practice that on your own. Now, when we think about the three types of forces, we have dispersion forces, and if you're listing all of the attractive forces, then dispersion should be your first answer for any molecule because everything has dispersion. Okay, now dipole-dipole interactions, those occur for polar molecules. And remember, something will be polar if it has lone pairs on it, right? Unless it's one of those few exceptions. So like a trigonal bipyramidal that has two lone pairs and forms a trigonal planar structure. Oh, no, sorry. Not that one, an octahedral. So if you have like an octahedral structure that has two lone pairs, then you form a square planar structure, I'm sorry. And so that would give you overall a nonpolar molecule. So there are a few exceptions in those expanded octets. For the trigonal bipyramidal, if you have three lone pairs, then you end up with a linear structure, which is nonpolar. Okay, but other than the few exceptions in the expanded octets, when you have a lone pair, typically it's going to be a polar molecule. Okay, So this right here indicates that NCl3 or nitrogen trichloride is going to be polar, and so we're going to have those dipole-dipole interactions. Okay, but hydrogen bonding, you would have to have a hydrogen and it would have to be bonded directly to that nitrogen. So we don't have hydrogen bonding for this first example, and so the strongest is the dipole-dipole moment. Okay, in our second example, we've got bromine. Okay, that's going to be 2 bromine atoms attached. And remember, halogens like to have 3 lone pairs. Okay, and you would find that that's all there is to that structure. So again, dispersion always exists. And now, in order for something to be polar, if you only have 2 atoms, something has to be different. Okay, so the lone pairs are not enough here. Lone pairs on a central atom will indicate that something is typically polar, but because we only have 2 atoms, there is no central atom, and so those are pulling evenly on either side of that bond. And so this is what we would call nonpolar. And so it's not going to have dipole-dipole or hydrogen bonding, and so the strongest force is going to be dispersion. Now NH3, ammonia, is going to be very similar to NCl3. The only difference is that those hydrogens will not have lone pairs. You'll only have the lone pair on the nitrogen atom. And remember, it's the lone pairs on the central atom that help you determine if something is polar. Okay, so the lone pairs on the external atoms, like those chlorines in that first example, those do not help you determine polarity. But that lone pair on that nitrogen does tell you that the molecule is polar, so you have dispersion, you have dipole-dipole, and because you have a hydrogen directly bonded to a nitrogen atom, technically you have 3 of them, then you have hydrogen bonding as well. And so hydrogen bonding is going to be the strongest. Okay, and then the last example, we've got CH2O. Again, your least electronegative atom is that carbon. Carbon does like to be the central atom whenever possible. Okay, and so we're going to bond the 2 hydrogens as well as the oxygen. Okay, and if we were to follow through with all of the electrons, and if we always work from the outside in, we would put all 6 electrons on that oxygen, but then we would realize that we're out of electrons and that carbon does not have an octet. Okay, so if we want to give carbon an octet, we would have to take 2 electrons from that oxygen and share them with the carbon to make a double bond. Okay, and so our final structure would be a carbon double bonded to an oxygen with 2 lone pairs on that oxygen, and it makes sense because oxygen likes to have 2 bonds and 2 lone pairs, and carbon likes to have 4 bonds, which it now has. Okay, so always everything has dispersion. Now this is a polar molecule, but it's not because of the lone pairs on the oxygen. Remember, another reason that a molecule could be polar is because the outer atoms are different. So the fact that oxygen is different than hydrogen, all right, that's what's making this molecule polar. Okay, so we're going to have dipole-dipole, and that is going to be our strongest force. So notice how we do not have hydrogen bonding in this last example because the hydrogen is not directly bonded to that oxygen. So hydrogen not directly bonded. To that oxygen, and so you're not going to have hydrogen bonding there. Okay, So in the next example, we're going to try to rank the following from lowest to highest boiling points. So remember, the weaker the force, the lower the boiling point. And so what they're basically asking us to do is to rank the following from weakest to strongest intermolecular forces. Okay, and keeping in mind that those go dispersion is our weakest. And then next comes dipole-dipole. And last comes hydrogen bonding. Okay, so if we're wanting to start with the lowest, then we need to find things that only have dispersion forces. And keep in mind that those are going to be our nonpolar molecules. Right, and our nonpolar molecules are going to be our hydrocarbons, so things that only have carbon and hydrogen. And so that would be this first molecule and the last molecule. Okay, and if we're trying to decide between the strength of dispersion forces, remember that the two things that can affect dispersion are the molar mass and the shape. Okay, so both of these are considered straight chains, and so the shape would not help us here, but the molar mass does. So remember that for dispersion forces, the smaller your molecule, the weaker the force, and then the larger the molecule, right, the stronger the force. So our lowest, and we'll just rank these with a 1, our lowest should be the 3-carbon chain, and then next will come that 5-carbon chain, right? So that's propane is the 3-carbon chain, and then pentane is that 5-carbon chain. Okay, so that leaves us with 3, oh, I'm sorry, I shouldn't have put a 5 there. It is the second lowest boiling point. Okay, so the 3 remaining, the next thing that we're looking for is something that only contains dipole-dipole interactions. And so it cannot have hydrogen bonding, okay? And that is going to be this second one listed here, okay? It's only going to have dipole-dipole. Right, and these first two only had dispersion. I'm just listing the strongest force that each one has. Okay, and it does not have hydrogen bonding because remember, there's not a hydrogen that's directly attached to that oxygen. Right, so no hydrogen there, and so no hydrogen bonding. Now, the last two both have hydrogen bonding, and when it comes down to this is what we call a carboxylic acid. And so carboxylic acids are known for having the highest boiling point, right? So that's going to be the highest, and then what we call an alcohol, that is going to come in at number 4. And the reason why a carboxylic acid has a higher boiling point, because both of these have hydrogen bonding, right, is because that hydrogen can technically bounce between those two oxygens. And so if I draw that carbon repeated here, right, we can have that hydrogen flip between those two different oxygens, and so we can get this very strong force, especially if we have 2 carboxylic acids coming in, where one is attracted to the hydrogen in one, and one hydrogen is attracted to the oxygen in the other. Okay, so that creates a very strong intermolecular force, specifically in carboxylic acids, and so they're going to give you the highest boiling point. So the more hydrogen bonding that you can have, the stronger the force. Okay, the next thing that we're going to look at is surface tension. So we're going to go through a few topics that just have to do with intermolecular forces and how these can be affected by intermolecular forces. So surface tension is a property of liquids that results from their tendency to minimize surface area. Okay, so minimal surface area is going to be accomplished by using spheres, and with fewer neighbors to attract them, those surface molecules are going to have higher potential energy than the molecules inside, right? So in the interior here in our picture. And basically, if you have stronger intermolecular forces, you are going to have higher surface tension. So that's what's important to remember here, is that the stronger your intermolecular forces, the higher your surface tension. And also keep in mind that if we raise the temperature of a liquid, that's going to reduce the surface tension. Okay. The next topic is viscosity. So viscosity has to do with the resistance of a liquid to flow, right? So if you're thinking of something that is highly viscous, you would think of something like molasses or maybe honey. Those are going to be your viscous liquids. And again, the larger the intermolecular force, the higher your viscosity is going to be. So we do have a few examples here. And just to kind of give you a little bit of a little bit of detail about what's going on is if you look down at the bottom, we've got bromine and mercury. So both of these are considered to be nonpolar, and so both are going to have just dispersion. Right, and so if they have just dispersion, and we were to look at the molar masses of these two, you're going to see that mercury has a much higher molar mass than bromine. Okay, so you're increasing in your molar mass, and so you're increasing in your dispersion force interactions, and so you're going to see that surface tension go up as well as that viscosity go up because you're increasing your intermolecular forces. Specifically that dispersion. And you can also see it occurring here where we have diethyl ether versus ethanol, right? You see that viscosity going up as well as your boiling point, and as well as your surface tension. And the reason why is because diethyl ether, remember, that's going to be the oxygen between two carbons. And so there's no hydrogen bonding, right? But ethanol is going to be those two carbons attached with an oxygen on the end, and that oxygen on the end does have a hydrogen. So that's a CH2, and this is a CH3 here. Okay, so it does have hydrogen bonding, and so you see an increase in everything, your surface tension, your viscosity, and your normal boiling point. Okay, also raising the temperature of a liquid will reduce its viscosity. Okay. Right, so you've seen this. If you heat up honey or something else that might be viscous, you'll see that it gets more runny. So as we're increasing the temperature of the water, right, we'll see that the viscosity will go down. Okay, the meniscus, remember, this is where you're looking at the curvature of a liquid, especially in a small piece of glassware. And so just keep in mind that depending on the type of substance that you have, that meniscus could be concave, so it could either go up concave would be down, or it could be convex and go up. Mercury is going to have a convex shape. It's going to have that curvature up this way. So this is your mercury on the left-hand side. But for things like water, you'll see that it's concave down. And this is based on the attraction to the glassware itself, right? So mercury is nonpolar, and so it's not going to be attracted to that glass tube. But water, with its attraction to the glass tube, is going to cause that to curve upwards so that those liquid molecules are attracted to that glassware and sticking to it rather than the water itself. Okay, and then capillary action, same way. So this is the ability of a liquid to flow up a thin tube against the influence of gravity. So again, you'll see capillary action happen for water, where it will climb up that glass tube, but you won't see it. It'll be capillary repulsion for something like mercury that's not attracted to the glassware. Okay. Very quickly, we're just going to review gases, solids, and liquids. I'm sure you remember this from your high school uh, physical science classes as well as Gen Chem 1, but your gases, those are going to have complete freedom in motion. They're going to move at random. They're going to be compressible, right? So it's going to expand to fill your container, or you can compress it down to a smaller volume. So it does not have any type of a fixed size or shape. And then solids, those are going to be compact, right? Those are going to retain their shape and their volume, or they're going to be incompressible, but they are still going to have motion because they still vibrate. And then liquids, remember, those will take the shape of their container, but it does have a fixed volume and it is not compressible. Okay, so hopefully you've also heard of phase changes. Remember, this is where you would go from a solid to a liquid or a liquid to a gas. And so this happens by changing the amount of kinetic energy in the particles enough to produce that phase change, enough to change it from, say, a solid to a liquid. Now, to refresh exothermic and endothermic processes, remember that exothermic is something that releases heat, and endothermic absorbs heat. Right, so things like melting, going from a solid to a liquid, that's going to require heat. A good way to think of this is if you have to put it on the stove and turn the stove on for something to happen. So if you want to melt butter or if you want to boil water, all of those are going to be endothermic processes and absorb heat. Something that releases heat would be the opposite. So things like freezing, that's why the back of your refrigerator is hot, right? Because it's releasing the heat from that freezing process, as well as condensation and deposition. And just keep in mind that sublimation is where you go straight from a solid to a gas. So that's here. Right, we're going straight from a solid to a gas. And then deposition is the opposite. Deposition is when you drop from a gas down to a solid. Okay, so when you bypass that liquid phase. So the weaker the intermolecular forces, the less energy molecules will need to vaporize. So just keep in mind that the weaker your attractive forces are, the faster that rate of evaporation will occur. So when you have the rate of vaporization and condensation occurring at the same pace, then you have what we call equilibrium. So there's no net gain or loss of either a vapor or a liquid. It doesn't mean that there are equal amounts of the vapor in the liquid, and it doesn't mean that the process stops of changing between a liquid and a vapor. It just means that the rates are the same. The rate of vaporization and the rate of condensation are equal. And so we have what we call dynamic equilibrium. Okay, so when the pressure exerted by a vapor, when it's in dynamic equilibrium with its liquid, we call that vapor pressure, or the pressure exerted by that vapor when we're at dynamic equilibrium. Okay, the weaker attractive forces that you have, the higher the vapor pressure is going to be. So basically, if you have weaker forces, then a substance is going to prefer to be in that gas phase. And also, if we increase the temperature, of course, we're going to increase that vapor pressure because we're going to increase the kinetic energy of the molecules. And again, they're going to prefer to be in that gas phase. And so we're going to have a vapor pressure increase. So heat of vaporization is going to be the amount of heat energy required to vaporize exactly 1 mole of the liquid. And remember that vaporization is always endothermic, and so our delta H values are going to be positive. If you had a question that was asking you about condensing, just know that condensation is exothermic, and so it may be asking for a negative value. It does depend on how the question is phrased. So if it says how much heat is released, then typically that negative is accounted for by saying the word released. But if it says how much energy without using the word released, then you may have to include a negative value in your answer. So just watch out when you see the word condensation, your values may need to be negative if the word released is not used. So as an example, we have how much heat is required to evaporate 100 grams of liquid ammonia at its boiling point if its enthalpy of vaporization is 4.8 kilojoules per mole. Okay, so these are similar to maybe some general chemistry 1 questions that you may have experienced with dimensional analysis. So basically, this is a dimensional analysis problem where your enthalpy of vaporization, remember that's your delta H vape, or delta H VAP, is equal to 4.8 kilojoules per 1 mole. Okay, so remember that this is what we call a conversion factor. Okay, so we never want to start with a conversion factor. Instead, we want to start with the other given information, which is our mass. Okay, so we have 100 grams of NH3, of ammonia, and they're asking how much heat is required. So at the end of this, heat is going to be represented either in joules or in kilojoules. Since they are giving us the heat of vaporization in kilojoules, chances are they want to know how much heat in kilojoules. Okay, so that heat of vaporization has kilojoules in the conversion factor, which means that we're going to want to use that as the last step in our dimensional analysis, which means that it tells us what the prior step must be, right? If we have kilojoules in the conversion factor that match our target, what we're looking for, then that means that we must start out with moles in order to use that conversion factor. Okay, so that helps tell us the middle step that we need to figure out the number of moles. And then in order to go between mass and moles, or between grams and moles, remember that is your molar mass. Okay, so that comes from your periodic table. So if you go to your periodic table and add up the molar masses for nitrogen and 3 hydrogens, you should get that molar mass to be roughly 17.03 grams per mole. Okay, so we have our given information, we have all of our conversion factors, and so now we can finally set this up. There's 100 grams of NH3. And then we've got to decide whether to keep or flip that molar mass. If we want the grams to cancel, then we're going to have to put the grams on the bottom. So that forces that 17.03 grams on the bottom with the 1 mole up top. Okay, so grams will cancel. And then looking at that enthalpy of vaporization value, if we keep it and write it as it is, 4.8 kilojoules per 1 mole. Now the moles cancel and we're left with the kilojoules that we want. Okay, now thinking about sig figs, the given information, our mass has 4 sig figs. Right, all those zeros are significant. The molar mass, we typically don't care too much about sig figs there because we could get more if we needed them. But our enthalpy of vaporization, that is only 2 sig figs. So we need 2 sig figs in our answer. And so that should round to 28 kilojoules. Okay, so we've been talking about vapor pressure. Just keep in mind that when a temperature yields a vapor pressure that is equal to the external pressure, then we start to have vapor bubbles forming anywhere in the liquid, and that is the phenomenon that we call boiling. Right, and the normal boiling point is going to be the temperature at which the vapor pressure of the liquid is equal to 1 atmospheric pressure. So the lower the external pressure, the lower the boiling point of your liquid is going to be, which is why if we go up into the mountains, say into the Rockies, the boiling point for your water should be lower. Now, just like heat of vaporization is telling us the phase change between a liquid and a gas, you have heat of fusion that is for the phase change between a solid and a liquid. So the amount of heat energy required to melt 1 mole of the solid is called the heat of vaporization. This is also endothermic, so these values will also be positive. But if we were talking about freezing, remember freezing could have a negative value if it doesn't specifically say that heat is released. So keep in mind that heat of vaporization values are typically going to be much larger than your heat of fusion values. So you can see here heat of vaporization should be typically much larger than your heat of fusion. Okay, so it takes a lot more energy to separate those molecules into the gaseous phase where there is a large distance between the molecules compared to solids and liquids, which are both relatively compact compared to a gas. Okay, and we've already touched on this. Just remember that sublimation, that's when you go directly from a solid to a gas, and deposition is the opposite if we go straight from the vapor to the solid. And this is going to happen when we have temperatures below the melting point, right? So before we ever get to a liquid, when we can go straight from a gas to a vapor. Okay, so the last topic that we're going to cover are heating curves of water. So here's where we kind of get into some calculations. You'll need to remember from Gen Chem 1 from your thermochemistry sections that heat is equal to the mass times the specific heat times the change in temperature. Okay, so you may have to go back and refresh using this equation here. People have abbreviated abbreviated it as MCAT, right? But we're going to need to use that equation when we are changing temperatures. And then the horizontal lines in this graph represent phase changes. And so if we're trying to calculate heat based off of a phase change, then that is going to be the amount that we have in moles times your either enthalpy of vaporization or enthalpy of fusion. And so on this graph, you can see that we're basically going to start out as a solid, right? So, and I think, yes, this is dealing with water. So remember that the melting and freezing point of water is 0 degrees Celsius, and then the boiling point of water is 100 degrees Celsius. So we're going to be a solid if you are at anything other than anything below 0 degrees Celsius, right? So from -10 to 0, we have a temperature change. And so during that section where we have a temperature change, that's where you would use that Q equals MC delta T. Okay, and then once you reach 0 degrees Celsius, you have to put energy in, but the temperature won't change because all the energy that you're throwing into the system is going into changing that ice to liquid water. So that's where you're going through that melting process. Okay, and so when it's a horizontal line, that's when you would use the Q equals N delta H, and specifically we would want to use the delta H of fusion there. And then at a certain point where you have converted all of the solid into a liquid, then as you put more energy into the system, you'll start to increase that temperature again. And so you can increase the temperature all the way from 0 to 100. Remember, this is going to be your liquid phase. So if you're at a point in that horizontal line, just remember that right there, and I'm running out of space, this is going to be both a solid and a liquid, okay? At this horizontal line, the second one up here, you're going to be both at a liquid and a gas. And so you can see that you've got both water as a gas and a liquid. Okay, and again, once you reach 100 degrees Celsius, all the energy that you put into that system is going to be to convert the liquid into a gas. And then once that has happened, then the more energy you put into the system, the temperature can then increase again as it is strictly a gas. Okay, so let's try some of these calculations. What is the total amount of heat released when 94 grams of water at 80 degrees Celsius cools to form ice at -30 degrees Celsius? So the first thing to realize here is that they're asking the total amount of heat released. Okay, so what that tells us is that we don't have to worry about the negative sign. It is assumed when we say heat released that it is going to be a negative value, and so we don't have to include the negative sign. It's just going to be the magnitude of heat. Okay, so now that we've got that out of the way, I think that it helps if you will draw a simple heating or cooling curve to see what's happening. So we're starting at 80 degrees Celsius. Okay, and we'll just kind of draw a graph here, and at the end we want it to be -30 degrees Celsius. Okay, so at 80 degrees Celsius, we know that water boils at 100, and so therefore it is currently in its liquid phase. Okay, so we're going to start out at 80 degrees Celsius, and then we have to drop down until we reach the freezing point of water. So right here, we're going to have 0 degrees Celsius, and so the first thing we're going to do is have a temperature change down to 0 degrees Celsius. Okay, so that's going to be step one. Then once we're at 0 degrees Celsius, we're going to have to put energy into the system in order to convert it from a liquid to a solid. Okay, and then afterwards we can decrease that temperature down to -3 degrees or -30 degrees Celsius. Okay, so we have 3 steps here. We have 2 temperature changes going from 80 to 0 and from 0 to -30, and we've got 1 phase change that's occurring. And remember that if we're going from a liquid to a solid, we're going to need that enthalpy of fusion. Okay, so we don't technically need the enthalpy of vaporization because we are not passing through the 100 degrees Celsius mark, but we will need that enthalpy of fusion. So in step 1, remember if it's a temperature change, you're going to use that Q equals mc delta T. And we will need to know the specific heat for liquid water as well as ice. Okay, so in this first step, we want to just make sure that we use the specific heat of liquid water, which is 4.184. That does come from your Gen Chem 1, but you should have that value available in a textbook or in an equations or constants sheet. So the heat for this first step is going to be equal to the mass, which they give us is 94 grams, times the specific heat of water, which is 4.184 joules per grams degrees Celsius, times the temperature change. And remember that that delta T should always be T final minus T initial. Okay, but we don't want to come out with a negative value. So it would technically be 0 minus 80, but we'll just want to switch that value to positive when we get there. Okay, and that is degrees Celsius. So your degrees Celsius cancel, your grams cancel, you're left with joules, and that should be 80.0. So that is 3 sig figs. So we do want 3 sig figs in our answer. And we get roughly 31463 joules. Now, if you notice the heat of fusion, those values are in kilojoules. So we probably want to convert everything to kilojoules. It just depends on how the answers are listed, but most of the time we're going to do this in kilojoules. So if we want to switch to kilojoules, remember there are 1,000 joules for every 1 kilojoule. So we've got to bring that decimal place over 3 spots. And so we'll get 31.4, right? 31.4 would be 3 sig figs. I'm going to keep 1 extra digit, and when I keep an extra digit until the end, but I want to acknowledge that it's not significant, I'll typically subscript it. So we get 31.46 kilojoules. That's 3 sig figs and 1 extra sig fig just to prevent rounding errors. So step 2, that's going to be our phase change. So remember our phase change equation is simply Q equals N times the delta H of fusion. Now the issue is we don't have the moles of the substance, we have the mass. So our first step is going to be to take that 94.0 grams of H2O and convert that to moles using the molar mass. And the molar mass of water is roughly 18. It's 18.02, and we do need to divide by the molar mass so that those grams cancel out and we're left with moles. Again, 3 sig figs for this as well, and we should get 31.3, and we'll keep 1 extra digit until the end, so that's a 5 afterwards, and kilojoules. Okay, so we've got step 1 here, step 2 here, and then step 3 is going to be similar to step 1. It's going to be that Q equals mc delta T. The mass doesn't change, it's still 94 grams, but the specific heat will change, right? Because now we want the specific heat for ice. And if you look that up in a table, it should be 2.09 joules per grams degrees Celsius. Okay, so just remember that that is the specific heat C of ice. Okay, and then times the temperature change. So in step 3, remember here, we're going between 0 and negative 30 degrees Celsius. So that would be negative 30 minus 0. And again, even though this value would come out negative, we're going to make it positive because we're just looking for the magnitude of the value. So on this last step, we get 5894 joules, but we're going to switch that to kilojoules, so we're going to divide by 1,000 joules per 1 kilojoule. And so that will give us a value of 5.894. Notice how that's significantly smaller than step 1, again, because the it's just going to take more energy in order to drop that temperature lower compared to the solid that we're only dropping the temperature by 30. And you also have a lower specific heat value for ice compared to liquid water. Okay, so that's in kilojoules. And then remember, if we're going to add up these 3 values, that's the last step, is to add them. It is based on the decimal place that tells us where we stop for significant figures. So the first 2 values stop at the tenths place, and then the last value stops at the hundredths place. Okay, and so the shortest place value would be the tenths, and so we're going to stop at the tenths place. So give me just a second and I will copy these over. So we had that 31.46 kilojoules plus 31.35 plus the 5.894. Okay, so vertically lined up, we can see that the shortest place value is that tenths place, and we should get 68.7 kilojoules for our final answer. All right, so that wraps up this video series and the end of the first half of this chapter.